Good morning. NASA's fifth rover to the fourth planet is 2 days away from landing. The mission's target, Jezero Crater, holds great promise for the Mars scientific community. However, getting to it safely is quite a challenge. Hello, I'm DC Agel. Welcome to NASA's Jet Propulsion Laboratory in Southern California. This is the first of several informative landing week media briefings on the Mars 2020 Perseverance rover mission. So let's get to it. Here to talk about the mission and some of the cutting-edge technology on board Perseverance, we have with us today Thomas Zurbuchen, Associate Administrator for the Science Mission Directorate, NASA Headquarters. Jennifer Trosper, Mars 2020 Deputy Project Manager, JPL. Adam Stelzner, Mars 2020 Chief Engineer, JPL. Trudy Cortes, Director of the Technology Demonstration Missions Program, NASA Headquarters. Arissa Stilley, Mars 2020 EDL Operations Lead, JPL. Jeff Sheehy, Chief Engineer of the Space Technology Mission Directorate, NASA Headquarters. And Mimi Young, Project Manager for the Ingenuity Mars Helicopter. For anyone who would like to submit a question, you can do so by using the Countdown to Mars hashtag. Our phone lines are now open for media. You can ask a question by pressing *1 and enter the queue. And we'll kick things off with Thomas Zurbuchen.
Well, thanks so much. I'm so excited to join the colleagues here from JPL as we count down to Mars. And we just recognize what an amazing journey this has been. And I want to thank at this time the team for working so hard on this mission, and especially in the past year in adverse circumstances. And I want to recognize the many sacrifices that the team had to do and really exhibited this true spirit of exploration that we always talk about. I just want to thank them for that. You know, Mars captivates our imagination and has been part of our dreams for many decades. And Perseverance builds on the long history of systematic, science-driven exploration of Mars that has been enabled by ever better technologies and systems. Right now, InSight is taking measurements of Marsquakes. Curiosity is focused on geological and chemical evolution near Gale Crater. And 2 orbiters are out there, new in the last couple of weeks, joining other orbits from NASA and other agencies, learning more about this planet. Our journey has been from following the water to seeing whether this planet was habitable, to finding complex chemicals, and now we're at the advent of an entirely new phase, returning samples, an aspirational goal that has been with the science community for decades. It is novel technologies that have enabled those breakthroughs we benefit today, and it's novel technologies that are enabling the next leaps of exploration, landing with more precision and safely, learn how to make oxygen from CO2 out of the atmosphere and more, and a true extraterrestrial Wright brothers moment with the Ingenuity Mars helicopter riding at the belly of the rover right now as we demonstrate controlled flight in a different world. We could, in fact, not land in Jezero Crater if it wasn't for the technologies that are already added to this. Mars is hard, and we never take success for granted. And as we want to land on Mars, it's because it's, of course, important. And we'll do so with cameras on, so the entire world is inspired with us. And as we do new and tough things and demonstrate these new technologies. Because whether it's on the red planet or here at home on our blue marble, science can bring us together and create solutions to challenges that seem impossible at first. And I'm really looking forward to turning it over to you, Jennifer, who is, of course, the Deputy Project Manager. Take it away, Jennifer.
Thank you. Well, I am so excited to be here today. I can tell you that Perseverance is operating perfectly right now, that all systems are go for landing. Last Friday night, we actually sent a command to the spacecraft. We call it the Do EDL command, Do Entry, Descent, and Landing. It makes it sound simple, It's not simple, but it enters the spacecraft into the timeline where it starts to do the entry, descent, and landing activities. So that was a very exciting event. The spacecraft is focused, the team is focused, and we are all ready to go for landing. Now, I want to tell you a little bit more about where we're at. So if you could bring up my first graphic. This is something that you can actually look at. It's called Eyes on the Solar System. And it tells you where different spacecraft are in the universe. And so we can tell you that Mars Perseverance is 125 million miles away from Earth, and we are only 370,000 miles from Mars. So we are getting there. The time it actually takes for a signal to go from Earth to Mars is 11 minutes. And so that's how we're communicating with the vehicle right now. And now, one of the things that we've been working towards is really making sure that the aim point we're targeted for at Mars, so we want to aim like on a dartboard, that the aim point is accurate. And so one of the ways that we do that is through these plots that you can pull up the next graphic there. This is called a navigation B plot. And the actual target, the bullseye of that target, is the green box. The green box, if we think we're going to target anywhere in that green box, everything is great. What you see are some colorful ellipses in the upper right-hand corner of that box. Those and the pluses in the middle, the pluses are where we think we're targeting, and the ellipses are the uncertainties around those. So that means, those ellipses all being within that green box, it means that the targeting is on the bullseye, and we are headed exactly where we want to be for Mars. Now, getting those navigation solutions is not that easy, and we need a lot of support from the Deep Space Network. So you can go ahead to my next graphic. The Deep Space Network has stations all over the world. There's some in Madrid, Spain, some in Goldstone, California, and some in Canberra, Australia. You can actually go to DSN Now, and you can see the real-time live shots, just like we're looking at now, to see which stations are operating and communicating with which spacecraft. And Mars 2020 is taking 2 stations right now in Madrid. So I want to thank all of the Deep Space Network operators across the world who've helped us. They've had 24/7 coverage for us for the last several weeks so that we could get such good data to have those perfect navigation solutions. So thank you. And now as I sit back, and this is my 5th landing. I've been on every rover that we've ever sent. I get that usual sort of anxiety, but very much excitement for what we're going to see. I look at the decades that we've spent building these rovers and building these teams to send these missions to Mars. And I want to talk about that just for a minute. I think back to Sojourner, the very first rover we landed on Mars. You can see this next graphic. Sojourner was about the size of a microwave oven, very small. And even though it's our oldest child, they're all kind of like additional children for me. It sort of behaved like a youngest child. It had a very free spirit, and it was just a fun mission to drive around. And then you can see the Spirit and Opportunity rovers were the next evolution. We built off of what Sojourner had done. Spirit and Opportunity actually could talk to Earth all by themselves. They still used solar panels, and they were these twins that explored all over Mars and outlived their lifetime by multiples of 10 and even 100, and they were just great rovers. And then we kind of took a pause and we really upgraded our systems. And you can see Curiosity down there in the lower left-hand part of this graphic. Curiosity, we went from solar panels to a radioisotope power source. The wheels increased in size. We could traverse over much larger rocks in different terrains. We had a sky crane landing system instead of airbags. I mean, we really made a step up. And then Perseverance, even though it looks a lot like Curiosity, is another technological step forward. And Adam is going to talk a lot about that after I'm finished here. And so in closing, the one final thing I want to talk about is it's not just about the rovers. And in fact, it's about the people who build the rovers. And it's not about the individual people who build the rovers. It's about all those individual people together, working together to make this mission work and all of these missions work. There are several dozen of us at JPL who've actually worked on all 5 of the rover missions, if you can believe it. And this next image is of the team. This is the Mars 2020 team, and there are many people who aren't pictured here, but I want to spend this moment to just thank the team for all of their work over the last almost decade to bring us to where we are today. The team isn't just a bunch of people who are all the same. It's a bunch of different, uniquely skilled personnel who know very deeply all the technical things they need to know in order for all those things to come together into a very complex system like the ones that we land on Mars. So thank you to that team. And I will end by saying, both for landing day on Thursday and for the whole surface mission, I wish that team great success that they have worked so hard to obtain over the last many years. And with that, I will hand it off to our chief engineer, Adam Stelzner.
Thanks, Jennifer. As Jennifer mentions, right, it is a huge army of human beings who have been working for decades in their careers to put us in a position to be able to put such a technological marvel as Perseverance on the surface of Mars. Here we see an image. This is on our first image here. We see a great shot, the hero shot of Percy. She is, looks a lot like Curiosity, but she's packed with a whole bunch of new instruments, science instruments. Those will be discussed a bit in depth next week, but we've got Raman spectrometers. We've got a technology for future human explorations to Mars, which Jeff will speak about a little later on today. She's big. She's a little bigger than Curiosity. Although she is a twin, she's a few inches longer, a couple of about 250 pounds heavier, and she's a lot more capable. Next image, please. As you watch the two of them together, Curiosity and Perseverance, they look similar, but you can notice immediately that the wheels are different. I'll speak a little bit about the wheels in a moment, but Percy's got a new set of kicks, and she is ready for trouble on this Martian surface with her new wheels. She's also much more capable at driving. You know, Curiosity needs to either drive or think about driving, but not do both at the same time. And we have used a piece of technology that we originally brought on for train relative navigation, a special visual processor to allow us to move Perseverance at 3 times the rate of Curiosity. Now, with all that movement, we had to reinforce her wheels. This is an image of Curiosity's wheels. She took a beating on the surface of Mars because of these sharp rocks called ventifacts. I have a model of Perseverance's wheel right here, and you can see it looks quite different than Curiosity's. As you see from this model, Perseverance has a gentle tread pattern. Next image, please. And that tread pattern not only makes her wheels more strong, if we go to the next image, it also makes them more capable. The soft tread redesign, we call that tread the grousers. You can go to the next image. Allow the wheels to be much more strong against rocks. Maybe we don't have that image. And also to have better performance in sandy terrain. Of course, driving is not the reason for the season. We have a sampling system on board, and this is why we're actually on the surface of Mars. You can roll this. You can see the robot arm and the coring drill that it has at the end of it. Our mission is specifically to be the first piece of a Mars sample return campaign. And in this leg, we need to take samples of Martian rocks. Inside that golden bit is a sample tube that looks just like this. This is one of the world's cleanest items, even though I just touched it. This is a model, of course. Hyper clean. Inside that coring bit, once we've cored it, we bring the sample tube and the bit inside the rover, and you can roll this image. This is our adaptive caching assembly. This is a small little robot inside the spacecraft, inside the belly of the rover, that manipulates that sample tube with the sample in it, moves it from station to station, confirms that we've got the right volume of sample, takes images of the sample, eventually seals the sample, and returns it for storage until we've accumulated a big enough cache to be ready to put it on the surface of Mars. Now, this progress, this forward motion in technology has not been a monolithic march. It's sometimes 2 steps forward and 1 step back. We know how hard the last year has been. Over the development of Perseverance, we've struggled with some technology challenges. Please roll this film. This is an example of an early technology test for parachutes called LDSD, and you can watch a parachute failure here that unfortunately calls into question the ability of our parachute to help Perseverance land on the surface of Mars. So we needed to stand up a supersonic testing qualification program for our parachute, which we did, and over the skies of Wallops Island, please roll, we had this image. And you can see our beautiful Perseverance's parachute, the same size as Curiosity's, but stronger, made of Technora, Kevlar, nylon. Beautiful, strong canopy is ready to slow Perseverance down in just a few short hours. So as we move forward, you can roll this, as we move forward through technology, we have overcome challenges, much as the nation has in this last year. NASA, over the last year, getting Perseverance to this place, has persevered. Our nation has persevered. Our world has persevered through these tough times. And this journey, this persevering journey of technology development is teamwork. It is a NASA-wide teamwork, and here to talk a bit about that, the Technology Development Mission Directorate is Trudy. Please take it away, Trudy.
Okay, well, thank you, Adam. You know, I just want to express a little bit of the sentiment that's already been expressed by Jennifer and Adam. You know, on behalf of NASA Space Technology Mission Directorate, we're absolutely thrilled to be partnered with our colleagues in the Science Mission Directorate, you know, leading this mission, and JPL, the multiple NASA centers who worked on this, industry, academia, some international collaboration went into this mission. And so we're just thrilled to be a partner with this on this next really truly groundbreaking Mars mission. STMD is quite proud to have 4 technologies, a record number for us flying along on the spacecraft and on the rover. There are 2 technologies that are landing instruments. One is a suite of sensors called the Mars Entry, Descent, and Landing Instrumentation. It's the second version that we're sending. The first flew on Mars Science Lab in 2012 with Curiosity, and it measures the conditions that the aeroshell will see. So it's about 28 sensors on both the heat shield and the back shell, and it'll give us data about the conditions that are seen with the hot gases, some of the winds that are seen, and it's really going to help engineers to reduce mass and optimize trajectory in the future. And then the new, really quite extraordinary capability that provides both hazard avoidance and precision landing at a site that's determined autonomously by the spacecraft, called Terrain Relative Navigation, or TRN. And this technology is a critical part of operations. It's actually operational during the entry, descent, and landing phase. We also then have 2 technology demonstrations on board during surface operations. One is to take data on the Martian weather in a variety of conditions. I like to call it the Rover's onboard weather channel. I'm coming to you today from Westlake, Ohio. We had 12 inches of snow overnight. And we could just a little bit of Martian weather sounds pretty good to us right now, just a little bit drier and a little bit hotter. The other technology that's part of surface operations is one that will convert carbon dioxide to usable oxygen. This technology is called MOXIE, and I find that that's very apropos, because if any rover we've sent to Mars has MOXIE, it's Perseverance. So with more science and technology on board than ever before, the number that I keep hearing is about 50%. I do mean that literally and figuratively. And you're going to hear more about MOXIE in a few minutes from Jeff Sheehy, the STMD chief engineer, who's going to talk to you about that. So for myself, as the director of a program that advances technologies for future exploration needs, Personally, I think one of the most interesting aspects is how the NASA team tested these technologies on the ground here on Earth to get them ready for flight. For example, with TRN that I just talked about, the precision landing technology, the JPL project team used some pretty unique ways to prove out the system performance here. First, they put the system through some typical environmental testing. So whatever the spacecraft is going to see on the way to its destination, mechanical vibration from launch, temperatures and pressures, which we call thermal vacuum testing, and then electrical compatibility to make sure when components are powered on, they don't interfere with each other, that type of thing. That's pretty pro forma for us. It's pretty standard. The second thing they did was focus on the software and algorithms, which are a huge part of TRN. So they did simulations in a lab to model the different scenarios that the system will see, when landing on Mars. And then next, if you could roll this video here, please. The team installed the system on a helicopter and flew it out over Death Valley in the Mojave Desert. It's really as good a simulation as we can get, where the system will identify known hazards that have been mapped, and then the maps are carried on board the system. Really close as we can get, and quite conveniently then closely located to JPL, so that was easy to run. Just like the system has to do on Thursday to get us to a safe landing spot in the Jezero crater. So then the final step in all this, and if you can show this next video, please. The team used suborbital rockets to take a next step. This was through STMD's Flight Opportunities Program. In fact, it was the Mast and Space Systems Zombie vehicle, which is a vertical takeoff and landing vehicle. And really, that was the final step to give decision makers, the comfort that they need to greenlight the system to be used as the primary system for Mars 2020's lander vision system. And those tests, by the way, I'll mention, took place back in 2014, over 6 years ago, which is another, just in closing, I want to make this point. This development that takes place over multiple years, all the technology development that goes into leading up to the mission, and then the demonstrations that actually take place on the rover when we land. They're really the primary way for us to continue to make these advancements that are so critical and required to send, more sophisticated robotic explorers, as well as humans, to places in the solar system we've never been able to send them before. And in closing, I'll say STMD, we say it often because we really truly believe it, technology drives exploration. And what I think is so great about Mars 2020, Perseverance, and Ingenuity is that they're all excellent examples of that happening in action. And we look forward to seeing all that action start on Thursday and taking place then. And so now I'd like to turn it over to Arissa, who's going to talk to you about even more about TRN.
Hi, I have the pleasure of coming to you from the mission support area here at JPL. So I'm just a few steps away from where I will take in Perseverance's landing on Thursday with some of my EDL colleagues here at JPL. Each team on Perseverance has a different perspective when we look at this beautiful ancient river delta that we see in Jezero Crater and the lake bed. The first two images I wanted to share with you kind of demonstrate this. The left side is a spectral data image from the Mars Reconnaissance Orbiter. So the scientists, right, they see the geologic diversity and the biosignature potential that we're looking for with this mission. The right side is an example of the EDL hazard map. And so for EDL, we ask the question, what could kill us on landing day? In the southeast are rocks that are strewn throughout the Jezero Crater landing site for us. The southwest and to the north, we have sand dunes. And then that beautiful river delta we keep talking about, well, that looks like a 250-foot cliff to us as we're landing, and we certainly don't want to land on that. This map is the best hazard map we have ever created for a flight mission. And it has to be, because this is the information that seeds the decisions that TRN is going to be making during Perseverance's landing. So what other improvements have we had to make to be able to go to a place like Jezero Crater? Over several missions, let's go ahead and show the next slide actually. You can see an improvement in the size of the landing ellipse. So some of those earlier improvements were based on the way that we do navigation. Curiosity had a smaller landing ellipse than historic missions because of something we call entry guidance, which is the spacecraft waking up when we start to sense the Martian atmosphere and start to steer our way through the atmosphere to a target. And this is actually an algorithm adopted from Apollo guidance that was used on the Apollo missions. The biggest difference for Perseverance since the Curiosity mission is using what we call range trigger. So this is a change in the way that we deploy our parachute. Curiosity deployed based on an estimated velocity, and for Perseverance, we're using an estimated range that allows us to more precisely control the distance from the target that we're doing that. And the effect it has is to shorten the longer axis or the major axis of our landing ellipse, which is why the Perseverance ellipse looks much more circular than previous missions. And this is also what allowed us to then start looking at places like Jezero, where it's harder for us to avoid the hazards. But as you saw on the hazard map, our ellipse is full of hazards. So let's move on through EDL and get to that part where we start to see TRN do its work. So I just mentioned parachute deploy. Now that we're on the parachute, if we can roll the footage, we've got one more beautiful parachute deploy video for you from the Aspire testing that Adam talked about. A few details about our parachute that we're flying. The materials are hand sewn and a mix of super lightweight nylon and really strong Technora that has a better strength to weight ratio than steel. When our parachute is packed in its mortar tube, it has the density of oak, and when we deploy it, it comes out at 100 miles per hour, has to inflate to a 70-foot diameter parachute in about half a second, and will put up to 60,000 pounds on the spacecraft and the parachute. And like so many other things within EDL, the parachute has to work. If it doesn't, it's not going to be a very good day for any of us. Once Perseverance is descending on the parachute, we can now release that heat shield that protected us during entry, and for the first time turn on the radar and start to look at the ground. And this is when we're ready to let TRN loose. TRN works in two parts. So if we go ahead and roll the next video. So the first thing we do is take images with a camera on board, compare those to a map on board, and then that allows Perseverance to reduce the error in where it thinks it is from kilometers to tens of meters. We do that with a really capable camera. The camera has a 90-degree field of view, and can you go ahead and roll the next footage that shows the feature matching? A 90-degree field of view, and has a oh sorry. Okay, I don't think we have it. That's fine. The feature matching you saw Trudy talk about, where it's comparing features back and forth between the map on board and the photos that are taken. We're able to do that quickly because the camera has like a 1/1000th of a second exposure, which allows us to get clean images while Perseverance is swinging around on the parachute, and it has about a 0.1 second readout, which allows us to spend less time taking or waiting on the image and more time processing it. The computer on board is also specifically built to do this work, so it's one of the fastest that we've ever sent on an interplanetary mission, built for space and for image-based navigation, which also gets to do some of that work, again, as you heard Adam talk about, on the surface when Perseverance is driving around. The second part of TRN is once Perseverance has a better sense of where she's at, she then uses a second onboard map based on where we can currently divert to at that point in time, and searches that area to find the safest place that she can fly to. That search is worth over 120 football fields worth of real estate on the Martian surface at that point. So Perseverance chooses that target, and then and that all happens in the 2.4 seconds it takes for Perseverance to send commands for us to separate from the back shell and start a free fall. So when we have that knowledge and we're done with our free fall, we fire up the rockets. I like to think of it as the jetpack or the descent stage that's attached to the rover, and start a divert to that safe landing point. We go from 170 miles per hour at that point down to around 2 as we slow down and get ready for the sky crane maneuver. So if we go ahead and roll the next, we throttle down 4 out of the 8 engines so that we don't impinge the rover during deploy. And this gives you a view of how that deploy looks during landing, where we both release the rover and then fire pyros that are going to release the landing gear or the wheels to get Perseverance ready to touch down. Once we're safely on the surface, the final 8 out of 158 pyros fired to release the bridles and the umbilical, the electrical cable that have been connecting the descent stage and the rover throughout EDL so that the descent stage can then fly away to a safe distance. And now we're on the surface of Mars. We have a brand new baby spacecraft in its new environment, ready to start rolling around. If we're lucky, the EDO camera suite that we've also got on board Perseverance this time will have been taking some amazing photos during those 7 terrifying or exciting minutes, and will give us some images of EDO that we've never seen before. With that, I'd like to pass it off to Jeff Shihai, who's going to talk to you more about MOXIE.
Well, thank you, Arissa. Coming to you from Northern Virginia, the suburbs of DC. Under normal circumstances, I would have loved sitting at the table there with the group and being at JPL to celebrate MOXIE landing on Mars with Perseverance, but these are not normal circumstances, so here I am. I'd like to talk about what MOXIE is, how it works, who designed and built MOXIE, how we'll operate it on Mars, and what we'll learn from it. So the full name of the technology demonstration is the Mars Oxygen In Situ Resource Utilization Experiment. Now that's a bit of a mouthful, so we pull a few letters out of that and we just called it MOXIE. In Situ Resource Utilization, or ISRU, means using the resources we find at the destination to produce useful commodities. If we're going to the moon, we'd have the resources that are on or the surface. On Mars, we have that, but we also have an atmosphere that we can use. The atmosphere is about 100 times thinner than Earth's atmosphere, and it consists mainly of carbon dioxide, about 95, 96% CO2, but we can use it. So MOXIE is a small-scale proof of concept demonstration of atmospheric in situ resource utilization, or ISRU. We have an animation of the MOXIE design that we can show. There it is. We can see that packed inside this gold-colored box are 3 main subsystems. There's a compressor to pull in the gas from the atmosphere and feed it into the system. There's a solid oxide electrolysis system, we call it the SOXY assembly, that does the chemical conversion. And then there's a collection of process monitoring and control sensors. MOXIE uses a thermal and electrochemical process to convert carbon dioxide into oxygen. At the cathodes in the electrolytic cells, CO2 plus 2 electrons become CO, carbon monoxide, plus doubly charged O anions. These anions migrate to the anodes, where 2 of them combine to become the familiar O2 molecule, with 4 electrons returned to the electrochemical system. The carbon monoxide byproduct is exhausted to the atmosphere. Something like MOXIE, any instrument you want to put on a spacecraft, starts out as a vision in the mind of a principal investigator. Principal investigator for MOXIE is Mike Hecht from MIT. He had a plan for what he wanted MOXIE to accomplish on Mars. Jeff Melstrom at JPL led a team of clever engineers who worked extremely hard and came up with several innovative solutions to implement Mike's vision in a way that would fit on the rover, survive the trip, including those 7 minutes of terror that we heard so much about, and work once it gets on the surface of Mars. We worked with a company called Oxyon Energy. They led a team that worked collaboratively with JPL and with Mike Hecht to develop the guts of MOXIE. That's that solid oxide electrolysis stack that I mentioned. A company called Air Squared led the development of the compressor that takes in the carbon monoxide atmosphere. Part of that effort was funded through the NASA Small Business Innovative Research Program. There's Jennifer highlighted the big team that worked on Mars 2020 and Perseverance earlier. There's no question that the team that designed, built, and tested MOXIE needed a lot of MOXIE to overcome all the challenges that were encountered along the way. There were times when some of the managers worried that the technology couldn't be developed in time to get it on the rover for delivery for launch. But as you can see in the next video, and I think it's up there, there's the beautiful gold box being lowered into the rover. So this is the day in March 2019 when MOXIE was installed into the belly of the rover. So there's a filter on the outside of the rover that takes in the atmosphere and feeds it to this box. The box utilizes the power system on the rover to power its operations. And so MOXIE was built and delivered on time, and it's in the rover on its way to Mars. It'll land about 50 hours from now, I think, just about. When we get it to Mars, MOXIE is scheduled to be turned on 3 times in the first 30 days or so of the Perseverance mission. The first time will be mainly to see if MOXIE responds to commands, and the second time will be to thoroughly check out all the subsystems. We'll heat it to the target operational temperature and apply operational voltages. And on the third run, we'll actually make oxygen under some conservative operating conditions. After that, during the mission of Perseverance on Mars, we expect MOXIE to have at least 10 opportunities to produce oxygen. Those operations will be distributed across times of the year, times of day and seasons of the year, because the Mars atmosphere varies with time of day and season of the year. So we want to see how MOXIE works under different conditions of the Mars atmosphere. For each of those operations, we expect to produce oxygen for about an hour at a rate of about 6 to 10 grams an hour. So you might wonder, why are we doing all this? What will we learn from MOXIE? What is this tech demo going to teach us? You can see in the image there a depiction of a first human landing on Mars. And one thing that stands out in that image, other than the obvious fact that humans are on the surface of Mars in that image, that's a big deal. But you can see on the vehicle, the landing vehicle, these big propellant tanks covered in gold-colored foil that serves as part of the insulation system on the liquid propellant. Liquid oxygen is an excellent rocket propellant, and for the return trip on eventual human missions, if we could make it on Mars, we wouldn't have to pack it into a launch vehicle fairing, launch it from the surface of Earth, push it all the way to the destination, and land it on the planet. MOXIE's, I might say that, when I first heard of this notion, I thought, I wouldn't want to be the first astronaut that's told you get to come home if you can make the propellants for the return trip. But actually, the MOXIE, the production capability for making the oxygen propellant will be put in place before we ever launched astronauts to Mars. So the vehicle that they needed for the return trip would be fueled up and ready for them before they even got there. Now, MOXIE, as implemented on the rover, is about 1% of the scale that would be needed to produce enough oxygen to fill up the liquid oxygen tank on a Mars ascent vehicle. So the reason we're doing a MOXIE is we'll take the lessons we learned in developing it and everything we learned from operating it on Mars, and we'll put together a plan to scale up the underlying technology, test that out, and then deliver it to Mars. Ultimately, as we build up a sustainable presence, first on the moon and eventually on Mars, various in situ resource utilization processes will be used to produce propellants or construction materials or life support consumables, even energy to power payloads. But leading the way will be MOXIE, which is the first ever in situ resource utilization demonstration on another planet. Now I'll turn it over to Mimi Ong, who will talk about the Mars helicopter.
Thank you, Jeff. So like MOXIE, Mars helicopter is a technology demonstration motivated by the potential to add aerial dimension to space exploration. So our team started with the question of whether it is possible to fly a helicopter at Mars, because the atmosphere there is extremely thin, 1% compared to what we have at Earth. So we systematically worked through a series of technical steps. And so we started with first demonstrating lift. Please roll the video. With a 1/3 scale vehicle here in a chamber of Mars-like atmospheric density, and somebody's outside trying to joystick this to fly. We achieved lift, but not control. We learned that the dynamics on Mars in this thin atmosphere is very different. And so next we built a full-scale vehicle with onboard real-time closed-loop control and demonstrated successfully for the first time ever a powered control flight in Mars-like atmospheric density. From there, we went on to build a full-up Mars helicopter, which will not only fly at Mars, but can operate and survive autonomously at Mars. And let's roll this video. And all the while weighing under 1.8 kilograms, that's 4 pounds. So what you're seeing on the video here is one of our many flights that we experimented with this 1.8 kilogram Mars helicopter. And you see the helicopter flying. It looks very easy when you look at it, but you're looking at a room with atmosphere about 1% compared to the room that you're sitting in right now. And those blades are working very hard, being controlled hundreds of times per second. So at this time, the Ingenuity Mars helicopter has been fully tested as much as we can on Earth. We have flown, we've test flown, and we have tested for environment. And next is time to demonstrate, prove, and learn how it operates at Mars. So to do that, at this moment, Ingenuity is approaching Mars, carefully held by Perseverance rover, and is accompanied by its base station, which is also riding on the rover, and so far so good. In cruise, we've turned on the helicopter temperature kept maintained as designed by the base station. We're maintaining the helicopter battery through the base station, and we are ready for EDL. And the day after landing, we'll turn on to check, confirm that the health is good. After that, the next major milestone will be when Perseverance rover delivers Ingenuity to the surface of Mars. If we could play this video, you'll see that the debris shield that protects the helicopter on descent is first deployed, and then the helicopter is deployed by what's called the Mars Helicopter Delivery System. It's a very intricate system that's going to take about 10 days to go through these series that you're seeing to drop Ingenuity to the surface. And that drop, the moment that drop happens, is the moment that Ingenuity has to start operating on its own in a standalone fashion. So this little 4-pounder, remember this entire vehicle is 1.8 kilograms, about 4 pounds, has to survive the cold, frigid nights of Mars, minus 90 degrees Celsius, keep itself warm. It has to garner energy from the sun through its solar panel to charge its battery. It has to talk to its space station. It has to do all of that in this little 4-pound. And the helicopter team will be working with the rover team and the scientists to look for the appropriate experimental site for our flight experiments. And then next, please. And now, after that, you'll see, after the rover deploys and drives away, there is Ingenuity helicopter. We'll have some tests of the rotor system for readiness, and then we will go for that very important first flight. Rover will stay at least 100 meters away and will be watching Ingenuity, and Ingenuity will take its first flight. The first flight will ascend to about 3 meters in height and hover for about 20 seconds. And it will perform the very first ever powered control flight on another planet. And as Thomas mentioned at the beginning of this event, it will be truly a Wright brothers moment, but on another planet. So after each of, and then if we can go on to the next step, please. So this is what we're looking for. So this is a picture of our Mars helicopter team. As Jennifer mentioned, it really takes teamwork. We're extremely tight. We've been working on this for over 6 years. Members from JPL, NASA AIM, NASA Langley of the ARMD, Revolutionary Vertical Lift Technology Program, industrial partners, AeroVironment, Qualcomm, Solero, and other companies. We've worked so hard. And so Shout out to our team. We're getting to Mars on Thursday. And every step going forward will be first of a kind and first step. So it'll be nail biting, nail exciting. So for all of you out there, on behalf of the Mars helicopter team, please join our journey. Back to you, DC.
Thank you, Mimi. We are ready to take media questions. Remember to press *1 to get put in the queue. And please direct your questions to one of our panelists. We're also taking questions through the pound countdown to Mars hashtag. And we have our first question from Marcia Dunn at AP. Marcia?
Yes, hi. Can you hear me?
Yes, we can.
Yes, for Dr. Zurbuchen, I'm wondering, if all goes well, what is the earliest year that you would anticipate getting these samples back? We hear just 2030, but I'm wondering what's the soonest year in the next decade? How does that compare to when the first human crew might arrive? And lastly, you know, Mars landings are always so full of tension and stress. Adding on top of that, the attempt to bring back samples, how much more is that magnifying, amplifying all the tension? Thank you.
Thank you so much for your question. So let me do them in reverse. The first one is, it's not adding stress. I mean, we always bet all of our we do always the best job we can. We bet on success. That's just what we do. And whether or not we want to return these samples is not adding to it. We're, of course, planning for that. That's exactly what we should be doing for this amazing mission. And for me, we're entirely focused on one thing right now, which is a successful landing. Frankly, we're not doing anything else with this team right now. They're focused on the successful landing. In terms of the earliest return, you, of course, have read both the work that we did and the independent review team, and they're telling us that basically launching in 26 and 28 kind of time frame is the right time to go there, which would bring the samples back in 31. And that, of course, is because of the planetary alignments, the home on orbit's going this way and in reverse, that set some of these windows that limit part of that, as do some of the propulsion characteristics of the spacecraft that are under consideration. So the early 31 is basically the relevant time. Of course, I just want to say where we are right now is in the middle, like we do every year, and there's certainly in positions and trying to make sure that we kind of bring all of our stakeholders along and make sure that we have the same enthusiasm for this mission. That includes the international stakeholders. Get this done in this time. The same is true for our human exploration of Mars, where a number of discussions are happening. Of course, the key element of the priority right now is to take humans out of low Earth orbit and really go towards the moon and kind of really make sure, as part of our Artemis program, we land on the moon and then build from there. So basically the earliest that we've talked in various plans and that have been talked about also in the previous administration is kind of late 30s, where such a thing could happen. But I just want to tell you what I'm talking about, bringing the community along, is really still happening, right? We have not had all the discussion with all stakeholders at the level of detail to really answer that question fully and with a lot of confidence. Technically, that's kind of no earlier than that we have talked about in the past. So that's how I would talk about those three.
Okay, thank you. Next up, we have Bill Harwood from CBS News. Bill? Bill Harwood from CBS News. Bill, are you on the line?
I am on the line. DC, can you hear me now?
Yes, we can. Thank you.
Sorry about that. So much for my AirPods. This is for Jennifer Trosper. Can you give us a sense of what we can expect after touchdown in terms of telemetry and imagery that would confirming a successful landing? I mean, some of this is in the press kit, but I'm trying to understand what we can expect that afternoon that we might get in time for evening newscast, for example, just kind of in general. And a related question, can you talk a little bit about how losing data or not receiving data for some reason might not mean something bad happened? In other words, if you went into a safe mode or something, why we shouldn't all be, oh no, you guys would obviously try a lot of recovery and all of that. Can you just kind of address that a little bit for us? Thanks.
Sure, I'd love to. So we have several telemetry streams that come down during entry, descent, and landing. The Mars Reconnaissance Orbiter is watching, and we call it a pseudo-bent pipe. So we get almost real-time data with the one-way light time from Mars Reconnaissance Orbiter through UHF. That should give us the most information. There are reasons that that could drop off during dynamic events while we're going through the entry, descent, and landing. In particular, you saw with ERISA, the mobility deploy. So it's possible we will lose data in that link, but it's also possible we'll get the data that has the most data, and that's where we would get some final, possibly camera images from the HAZCAMs on the front and rear in that data. We also have X-band data that goes direct to Earth, and in that we get some tones. Those tones just tell you what key events have happened, parachute deploy, for example. So we hope to get that. Earth does set shortly after landing, and so depending on horizon masks, it's possible that we would lose that link as well. After we land, we hope to get either of those links. We also are recording data with the MAVEN orbiter, so we will have data that we have to process and we'll get within several hours after landing. But then even if we don't hear anything at landing, if some of those data links drop out, we do have our first overflight of another orbiter, the Odyssey orbiter, about 3.5 hours later. And that's a small data volume pass, but getting that pass would get a lot of information about the state of the vehicle. If it's able to communicate, then landing was safe. After that, we have another pass in a few hours. It's about 6:30 p.m. on landing day where we would get some more data. So if all goes well, we could potentially see some images by the end of the day. If not, it's possible that something happened that caused the vehicle to go maybe into a safing mode after landing. If we're in a safing mode, then we have fewer passes, we send less data, and some of our fault responses. So the rover's programmed, and we spend a lot of our time thinking about what could go wrong and how do we help it save itself. And so one example is if something went wrong with the main computer, it could take up to a week for the rover to go through all the autonomous actions that it's programmed to do, switch through all the telecommunications hardware, and then switch to the other computer. So there's a lot of investigation. We will look at everything, look at all these different, we have UHF stations, we have X-band stations on Earth looking at the spacecraft. So we will work very hard to understand the success, and if something went wrong, to figure out how to get the spacecraft back if possible.
Thank you, Jennifer. Okay, next up we have Chelsea Gold from space.com. Chelsea?
Hi, thanks so much for taking the question. My question is for Jennifer. Everyone talks about the 7 minutes of terror, which obviously sounds intimidating, but as someone who has worked through all of the rover landings from NASA thus far, you seem more than prepared for the couple days ahead of us. How are you feeling 2 days out, anticipating yet another, fingers crossed, successful rover landing on Mars?
I'm feeling great. There are no guarantees in this business. There are we always talk about what Mars might throw at us this time, and it's never the thing it threw the last time, and so we have to be prepared for that. But I tell you, I look at those navigation solutions. We did our last time to target Mars was trajectory correction maneuver number 3. We've never been able to not do the last 2 maneuvers and still be within our bullseye target. So the team is doing a great job. The spacecraft is solid. I led the test program. I feel very confident that it will do the things we do. But again, no guarantees, but I'm feeling great.
Thank you, Jennifer. Again, let's see, we have Joe Palca from NPR. Joe?
Hi there. Quick question about the navigation system, the terrain relative navigation system. Does that have a dedicated camera? And if so, is there a similar sort of camera doing the same thing for the rover once it's on the ground? And where is that camera? Is it on the sky crane or is it on the lander? I don't know who should maybe. I'm not quite sure. Trudy or somebody.
Trudy, you want to take that?
I'm not sure if ERISA wants to take that.
Either way.
Yes, it does have a camera system on it, but ERISA might be able to give you more details about it.
ERISA?
Yeah, so as we said, or as I said before, there is a dedicated camera for the entry, descent, landing part for terrain relative navigation that we call the LVS camera, or Lander Vision System camera. And if you looked at a picture of the rover, it would be sort of under the front left armpit of the rover looking down. And the computer that is in charge of doing the image processing and helping to get us to a solution we refer to as the VCE, or I think the visual, and I'm going to get in trouble now if I misremember, but I think it's the visual compute element. And that computer is the same one that's used on the surface on the rover for when it does autonomous navigation. The cameras that the rover uses to do that are different. So we have navigation cameras that are on the mast of the rover. So they're the ones similar to what Curiosity does. Those will take photos of where the rover is, along with the hazard avoidance cameras that are on the front, lower on the front and rear of the rover, and can combine those images to enable the autonomous driving on the surface. So there's different cameras for those purposes, but the same computer is doing the work.
Thank you.
Great. Thank you, Arissa. And now we're going to go to a question from social media. JS on Instagram asks, how does NASA test for the different atmosphere of Mars when practicing on Earth? This might be good for both Adam and Mimi.
Sure. Okay, so for helicopter flight, what we did is we used the space simulator at JPL. It's a 25-foot diameter chamber, about 70, 80 foot high. And we pumped that chamber down to near vacuum, and then we backfill with carbon dioxide to about 1% density in atmospheric density compared to outside of the chamber, compared to Earth's. And that is representative of Mars, and we've been doing all of our flight tests in that. So that takes care, for flying a helicopter, that takes care of the atmospheric density. The second part is the gravity. The Mars helicopter will experience only about 40% gravity at Mars, and when we're testing on Earth, it weighs a lot more. So what we do is we attach a gravity offload on the top to take care of the difference between Mars and Earth gravity. So that's how we simulate Mars on Earth.
Thanks. For parachute testing, we go to very high altitudes in the Earth's atmosphere, so we get the right atmospheric density. Of course, because we're here at Earth, we have the wrong ratio of specific heats, we have the wrong speeds of sound, so we need to adjust our testing program as best we can to get the parachutes to open up in the right fluid mechanical configuration and states here on Earth. And we do the best we can, very high altitudes with supersonic rockets that get us up there.
Thank you, Adam. And next we're going to go back to the media on the phone. And next up we have Paul Brickman with UPI. Paul?
Yes, thanks. Hi, can you hear me?
Yes, we can.
Okay. So regarding coming in through the atmosphere, so Perseverance is like Curiosity, but heavier. Can you describe how the capsule steers itself during entry, and or if it does steer itself? I know that it has at least one ballast device that it drops, and so wondering if someone could say how those work, and if that is what dictates the angle of entry, and can the capsule make any adjustments during that time?
Arissa, question for you?
Yeah. So the way that we do that is very similar to Curiosity. The main differences are when those devices were designed for the vehicle at Lockheed Martin, they have some flexibility in how much mass you put into them. So before we start entry, I think shortly after we separate from the cruise stage, about 10 minutes before entry, we actually will eject two masses that are called cruise balance masses, and that's what allows us to shift the CG. So on the way to Mars, we're spinning, right? Our CG is as centered as it can be. And then we release those cruise balance masses that cause our CG to have an offset, and that's what provides the lift vector that we use to steer both Curiosity and now Perseverance through the atmosphere. When we get to the end of that phase, we similarly eject now 6 smaller masses called the entry balance masses, and that's to put that center of gravity back to the center pretty closely before we deploy the parachute, so that we're not deploying the parachute at a big angle. So the way that we do that is very similar to Curiosity. We just adjusted the masses and took and did it that way for Perseverance.
Thank you, Arissa. Next up is Gina Sinceri with ABC News. Gina?
I'm not sure who can take this, but I know you have other assets from other countries orbiting Mars. How are they contributing to this?
Thomas?
So yes, there's a number of assets from other countries. Basically, in this entry, descent, and landing, the only assets that actively contribute are U.S. assets. We do not, for the immediate entry, descent, and landing activity, are relying on other assets. But Jennifer, I'm going to kick it to you to see whether there's fallback solutions and which other assets would be used. Jennifer, go ahead.
Yeah, so on the first sol, we call it sol 0, the latest afternoon pass that we get, it'll be about 6:30 p.m. Pacific time. That will be with the Trace Gas Orbiter, the European asset. And so they are supporting this mission by relaying UHF data to us. So we appreciate that.
Okay, thank you. Next up, we have Jonathan Amos with the BBC. Jonathan?
Hi, DC. Greetings, everybody from London here. Can I just check, Jennifer, that you're not going to do a correction at all going into Thursday? Now, you're tucked right up in that top right-hand corner of that box. You're obviously comfortable with that. And then the other question I had, just going back to Curiosity, what's going to happen on Thursday? What should we expect to see? We remember Adam walking around the control room, and Alan Chen was the voice that we heard calling Curiosity down. Alan tells me he's not going to call it down this time. I wonder whose voice we're going to hear calling Perseverance down on Thursday.
Okay, I'll take the second one. I will answer. Swati Mohan will be calling Perseverance down. She's a guidance, navigation, and control engineer who's been working tirelessly on entry, descent, and landing. She is one of Al Chen's deputies. Al Chen will be in there as well. He'll be giving the final calls of touchdown, nominal, and things like that. And Swati will be giving the intermediate calls. So that's our EDL team. You'll notice a few differences. We'll be socially distanced. We'll have masks on. There will be fewer people in the mission support area. We actually, fortunately, have a second floor where we have a large number of folks as well, the surface team and the EDL, the entry, descent, and landing teams, who will be on site as well. So we're spread out, but we have a lot of folks here. Back to your first question about are you really not going to do another maneuver? You're up in the upper right-hand corner of your targeted box. Is that good enough? Well, yes, we believe it is. Now, we have, if we got it really wrong, we still have the ability to do another maneuver if we need to. But those ellipses are the uncertainty ellipses on our estimates. And all those ellipses are still well within the green box. And the green box is conservative. So we have high confidence that we won't have to do another maneuver, but we're always ready. We have daily tag-ups twice a day to talk about whether there's something that we don't like about the navigation data. The plots are coming out all the time. So we are looking very closely, and if we need to do something, we will, but we don't expect that we will have to.
Thank you, Jennifer. Okay, next up we have Irish Television's Leo Enright. Leo?
Thanks very much indeed, DC. I wanted to ask a couple of questions about the terrain relative navigation. This is a technology demonstrator, yet it is also mission critical. So I'm wondering, how unusual is that? Is this something that's happened before, regularly perhaps? And I'm wondering, with a technology demonstrator, is there a plan B? Has the Sky Crane been told that if something goes wrong with the TRN, that it should make some sort of Hail Mary landing? And if I may also very briefly ask about this 120 football field size area that Arissa spoke about, could you just clarify the hover time available with this system. If you're coming down, if the sky crane is coming down on the home touchdown line, you just plonk it down. But if you have to go all the way over to the other end of the field, how long can you stay in the air is my question.
Well, Leo, as always, a very detailed question, and thank you for that. Let's first start off with Thomas Zurbuchen.
Yeah, I'm just going to, before we go into technology, which I'm not the right person, I just want to tell you that, yes, we have, when we landed with Curiosity, kind of done a number of technologies for the first time. Terrain relative navigation is not an exception. What I just want to tell you how we did this when we chose Jezero as the place to go because of its amazing science promise. We actually did so with an asterisk attached to it, which is basically we said we want to do an independent review based on the data and the planning that the team had put ahead of them to make sure that this technology works. And if the answer would have been from that review, we're not quite sure, we would have backed off into another landing site. And we were convinced, I was convinced, that the technology was ready to go. So the way we're doing this is using the rigor and using data to drive processes in a way that we can include these technologies, and we're proudly doing so. Now over to the specialist on technology.
Okay. Leo, did you have a follow-up?
I think there were...
Yeah, I was just wondering about a plan B. Is there some sort of Hail Mary landing that can be done if for some reason, say, the TRN cameras don't work or something like that?
How about Adam Stolson, the chief engineer?
Sure. Leo, we have, if TRN does not work, does not converge, and we don't get a TRN solution, we would go to a normal MSL Curiosity-like divert maneuver, and we would have a increased risk of terrain hazards, but a risk that we took eyes open at the Jezero landing site. So, yeah, there you go.
Okay. Thank you, Leo, and thank you, Adam. Next up, we have Jackie Goddard with the Times of London.
Hello, thank you. So we've grown to know a lot about how the spacecraft work. I wondered if you can give us a little insight, one of you, into how you folks work. I'm referring particularly to what you have to do over the next few weeks and months to keep yourselves on Martian time. So the sleep shifting, I think some of you wear special watches. Could one of you talk about that, really? What adjustments do you have to make to how you live and work in order to become a Martian? Thank you.
Jennifer, you want to take that?
I will take that. The surface team, so there are about 350 people and some additional scientists who will be working on Mars time. So right now they are adjusting their clocks. The way that we work is we typically will show up in the afternoon on Mars because that's when the data comes to Earth. And then we will work for 12, 14 hours until we get the uplink to send to the rover based on the data that we received. Now, the Mars day is 40 minutes longer, so that's what makes Mars time hard. So if you're up at, will probably be 2 p.m. will be our start time, and then that will adjust by 40 minutes every day, which for a while it works. We've kind of found that we only ask people to do this for 3 months. The first cycle, there's a 37-day cycle that you go through, and then you're kind of back to the original time. The first cycle, everybody's excited. This is cool. I'm on Mars time. And, you know, in fact, last on Curiosity, one of our engineers took his whole family on Mars time because it was summer and they weren't in school. And so we had this whole family on Mars time. By the next cycle, people start to get a little bit tired, and by the third, by the time we finish Mars time, they are well ready to be finished with Mars time. It's hard on your body. It's like being jet lagged. And so everybody, we have different things that we allow folks to do if they need to stay local, or we have cots in offices and things like that to just help people manage in Mars time. The reason we do Mars time is because it is the most efficient way to have the rover make progress on a day-to-day basis, and that's really important early in the mission to get it kind of unbuckled and ready to go for the great science mission that we have.
All right, great. Thank you, Jennifer. Let's see, we're going to go to a few more social media questions. Jeff, apparently social media really is interested in MOXIE. We've got two of them for you. The first one is from Glenn on Facebook, who asks, could MOXIE generate anything other than oxygen?
No, MOXIE is specifically designed with the electrochemical system and the elements in that to take carbon dioxide and generate O2 molecule. There's all sorts of electrochemical processes that are used industrially, even very large scale here on Earth to make all sorts of things, but each of them are tailored for a particular purpose. And this one's designed not only to make oxygen from CO2, but to do it under Mars conditions.
Great. And the follow-up, Daniel from Facebook asks, is NASA starting to terraform Mars using MOXIE?
Yeah, that's a good, interesting question. Good question. And there's a lot, in the literature about terraforming, ranging from, fairly serious studies to science fiction sorts of works. And it's a dream of a lot of people to take another world and turn it into something that's more habitable or more like we're familiar, something we're more familiar with. I talked about scaling up MOXIE. The MOXIE, as we're sending it to Mars on Perseverance, is very small scale. It's going to make a little bit of oxygen. It's really going to prove the concept. I talked about scaling it up 100-fold or so to fill a propellant tank. If you were going to try to produce large amounts of oxygen or to take large amounts of CO2 out of the atmosphere, MOXIE wouldn't be the type of technology that you'd use. It's a fairly power-intensive technology. It's good for the purpose that NASA envisions for atmospheric IRU, atmospheric ISRU on Mars, but there are a lot of other technologies that people have written about. I'm not an expert in those, but in terms of either carbon sequestration, which is something or CO2 removal, which is something we may be interested in here on Earth, or generating life support consumables to change the atmosphere of another world. The solid oxide electrolysis wouldn't scale well to that sort of implementation.
Thank you, Jeff. And Thomas Zurbuchen.
Yeah, let me just add a couple comments. So first of all, the answer is no. This instrument, and I think you said that with more words. The answer is we're not terraforming. We're terraforming, or we're shaping the environment of Mars as little as a mouse in Nevada is changing the Earth, right? It really is not. It's not a substantial kind of global impact of what we're going to do, and we have no intent. We think Mars is a beautiful planet that remains to be discovered. And I just love the path ahead that you just outlined of trying to scale that up so we can do more exploration with more people, with more systems, and even with those, the overall system of Mars would not substantially change. And no plans that we have in a large scale would create a large scale change on this planet.
Thank you, Dr. Zurbuchen. Okay, that's it for this morning's news briefing on the Mars 2020 Perseverance rover mission. If you're a member of the media and have further questions, please call JPL's Digital News and Media Office. We'll also continue to answer questions on social media as well as online. Thank you for your questions, and thank you for the panelists for joining us today. A reminder, at 12:30 p.m. Pacific today, there is a media briefing that takes a deeper dive into the science of the Mars 2020 Perseverance rover mission. And then tomorrow we have two more briefings, both in Pacific time. The first one's at 10 a.m. when we will have an overview, actually a more deeper dive into what's going to happen during landing. And then there will be one at 12 p.m. where we will be talking about searching for signs of ancient life and Mars sample return. Perseverance is set to land on Mars on February 18th with commentary beginning at 11:15 a.m. Pacific